You want to start at the beginning, or do you have a specific spot you want to start?
I think let's start at the beginning, see how it goes.
Okay.
The first one shouldn't be so bad.
Well, as long as you know the technique on this, then it's not bad.
Yeah, I think this one might be very easy.
Okay. What's the first step?
Okay, you can subtract 10 from both sides. And
Now,
then you can...
notice that that's not usually what you want to do with a quadratic.
Yeah.
Notice right off the get-go that you have a quadratic. And in a quadratic, you usually want everything on one side and 0 on the other.
Oh, yeah. So instead, let's just...
so think about factoring.
Yeah. So
that's usually what we want to do with a quadratic, is factor it.
X minus 5, x minus 2 is less than or equal to 0.
Now, the next step is critical. In other words, whether I have the product of two functions, or even if I had something like this, there's a step that you have to take next in order to solve it. It's called a sign chart.
Oh, yeah.
Okay. The first thing you have to do with a sign chart is what? You have to determine what about this inequality.
What's a positive and what's a negative?
Well, first of all, before we can do that, we need to determine the critical points. And the critical points are whatever makes that 0, or that 0, or if you had something in the denominator, whatever made the denominator 0. So those are your critical points. So what are the two critical points here?
2 and 5.
Okay. So I'm going to put 2 and 5 on there. And I'm going to get rid of the 0 because it really is just more confusing than anything else.
Yeah.
Now what's the next step?
We find what's negative and what's positive.
Right, but the thing is that we need to test a point that's to the left of 2. We need to test a point between 2 and 5, and we need to test a point to the right of 5. And that's it. And that will tell us the entire sign chart for this function. So what's a good point to test to the left of 2?
Negative 3. I mean, 2, 1 or something? Just anything really.
How about 0? 0 is the easiest. Any point to the left of 2 will do.
Yes.
So when we use 0, we get a negative there. We get a negative there. The product of two negatives is a positive. So I write positives everywhere to the left of 2. Now let's pick a number between 2 and 5.
3.
Okay. 3 gives a negative there, positive there. The product of that is a negative. So anything between 2 and 5 is negative. And a number to the right of 5, like 6, produces positive, positive. So now, what is the answer in interval notation to the question, when is that less than or equal to 0?
So that would be 2 to 5.
Brackets or parentheses?
Brackets. So,
And that's how you do inequalities based on, products of linear functions or quotients of linear functions. And I really don't know another way of doing it other than using this sign chart. You may have learned a different technique, but that's the only one I know
of. All right.
Okay.
Yeah, we learned sign chart.
Okay, good. All right, let's look at the next one here. Specify any axis or origin symmetry of the graph.
Would that be symmetry around the origin?
Yes. Yes, exactly. Exactly. And the way you can tell symmetry about the origin is if you rotate it about the y-axis and then again about the x-axis, you have the same thing as symmetry about the origin. Or you could rotate it about the x-axis first and then rotate it about the y-axis. And that's, if you do that, to that, you get this. And that makes symmetry about the origin.
Okay.
Which makes it an odd function also. Symmetry about the origin is odd, as opposed to symmetry about the y-axis, which is even.
And what about the x-axis? Is that also even, or is that all?
Neither. In terms of odd or even functions, you have either symmetry about the y-axis or you have symmetry about the origin. But symmetry about the x-axis does not equal an odd or an even function.
Okay.
Okay, here we have a problem that we can do a couple of different ways. We can do it the hard way, or we can do it the easy way. Although I'm not sure it's that easy. They want to know what the inverse function evaluated at 14 is. So how would you think we would do this?
So let's think the inverse function, would that be 1 over 3x minus 1?
No, how do we find inverse functions?
Oh yeah, you switch the y and the x.
And then solve for the new y. So there's the inverse function. And then to evaluate this at 14, what do?
You plug in 14 for x. So
f of 14 would equal, f inverse of 14 would equal 5. Now, let me show you something that will come in handy when you go to take calculus. And that's how to solve this the easy way. If f inverse of 14 equals 5, then I know that f of 5 equals 14.
Oh, that is helpful.
There's my answer immediately. Hold on a second. Did I say that right? If f inverse of 14 equals 5, then f of 5 equals 14, and we can certainly see that if I put f of 5 in there, it's equal to 14. What I'm trying to get at is the inverse function, you merely switch the domain and range. Notice that all I did was switch those two. I know that f of 5 equals 14 if f inverse of 14 equals 5. And so since they're asking Oh, hold on a second. Just a second. We started with this. That's why I was confused, as we already had an answer. If I'm trying to solve this problem the short way, then I know that f of some value is equal to 14. Right?
Yeah.
And whatever this question mark is, that will be my answer to their question. Well, if I go up and I look for what is equal to 14, that would be 14 is equal to 3x minus 1. 3x is equal to 15. X is equal to 5. So immediately I know that it's 5 and 5. Now, whether that's easier than solving for the inverse, I don't know. But when you get to calculus, there will be applications where this principle is important. The most important principle to learn is that if f inverse of 14 equals 5, then f of 5 equals 14. All right. Let's start with A. So that is f of x. What is f of minus 2?
That just be negative. So I could look at the graph and find
That's what they want you to do. In other words, they want you to look at the graph and find out what f of minus 2 is.
Okay, so that'd be minus 2 for y then?
Correct. And let's look at B. What is f of 0?
F of 0 is 0.
See that open circle?
Sort of, yeah.
In other words, if you look at this open circle right at 0, comma 0, that means f of 0 is not evaluated there. F of 0 is actually occurs right there. It appears to be negative 1/2. Let me blow this up just a hair. Now can you see that that's an open circle right there, and that if you're evaluating f of 0, you have to go to this point right there, which is about minus 1/2 on the y-axis. Okay? What is f of 2?
F of 2?
Approximately.
Roughly 2.
A little bit less than 2.
Yeah.
What is f of 3?
F of 3 is 0.
And that is evaluated because it's a closed dot. In other words, if it's a closed dot, we can evaluate f of 3. If it's an open dot, we can't evaluate it from this part of the graph. We've got to go all the way down to this linear part down here. Okay, determine the domain of f from this graph.
So that would be negative 4 to 4?
To 3.
To 3, sorry.
Okay, you see, because we're looking at the x-axis.
Yeah, just...
Okay, and what's the range of this graph?
The range is negative 4 to negative 1/2, and union is 0 to 2.
Good. With parentheses around the next to the 0. And brackets, in other words, the range is negative 4 bracket to negative 1/2 bracket in union with parentheses, bracket, because it can be 0 at this point over here, comma 2 bracket. So everything's bracket.
Okay.
All right. Yeah, it's definitely, you're getting into calculus type stuff. This is the kind of questions you learn or that are very pertinent to calculus, because we're very concerned about continuity and differentiability.
Would you say the courses are very different?
Oh yeah, calculus is significantly different than any other math you've taken. What differentiates calculus from everything else is the concept of limits. And even though you haven't touched on limits yet, that's where calculus starts, is when you get into limits. And then there's differential calculus and integral calculus. And that's just a completely different kind of math. It's a culmination of algebra, geometry, and trigonometry, and a couple of other pre-calculus subjects. But you put all of those together and you end up with calculus. And what they say is that calculus is the greatest math developed, the most useful math development in the history of mankind. It allows us to do more things in real life because of the development of calculus than we ever were able to do before so. So it's very valuable. Okay, so what is the domain of this function?
The domain for that one is negative infinity.
Domain. X values.
Are those lines going on forever, or is that fixed?
You know, I don't know. If they're meant to go on forever, then it's negative infinity to positive infinity.
Yeah, because it doesn't. The lines don't have a point on the end.
I can't tell. From the previous graph, it felt to me like this thing begins there and ends there. So there wasn't much question about the domain here, but the fact that there is neither an open circle or a closed circle leads me to believe that these lines go on forever. So I would say negative infinity to positive infinity.
Yeah.
What's the range?
That would be -1 to positive infinity.
No, look at the graph. We're looking at what the y values can be.
Oh. This would be -1, and that'd kind of be on its own, yeah, in union with 1 to infinity.
With a parentheses around the 1.
Yeah.
Express the area of an equilateral triangle as a function of x if the side length is 3x.
Okay.
Now you can do this two ways. We can do it the hard way, which is to figure out what the altitude is and calculate the area as 1/2 the base times the altitude, and it will be a function of x. There's also a formula for the area of an equilateral triangle as a function of one of its sides, which would be considerably easier. In other words, you have the area of a triangle as 1/2 base times height, but you have the area of an equilateral triangle as, I believe it's square root of 3 over 2 times the side length. But let me just check that. Actually, it'd be easier for me to calculate it than it would be to check it. But all of a sudden I'm there. No, I'm not there. Let's figure it out. Let's calculate it ourselves.
Okay. So we use the root 3 over 2 then?
Well, let's not use this because I'm not positive about it.
Okay.
And figure out what the area of this triangle is.
All right.
This triangle here is a 60-30, and this base here is 1.5x. So what is this altitude here, or height?
Let's see. So
Here's our normal 30-60, whose dimensions are 1, root 3, 2. So in this case, opposite our 30 is 1.5. So what is opposite the 60?
that'll be root 3 times 1.5.
Okay, 1.5 root 3. And now the area of this triangle is the 1/2 the base times the height. Huh. And it's not what I thought it was, but it's still, it's 1.5 times 1.5, which is 2.25 root 3 x. Excuse me. Yeah, there's the x right there. And in fact, oh, hold on a second. That's also x.
So the x squared then.
Making it x squared. So the area would be, now I do need to look it up, just a second. Now I'm curious as to what, where's this going to be? It's going to be in the chapter on trig. Area of an equilateral triangle. Gosh. No, I'm not sure where that is. Area of an equilateral triangle. It's funny, the more math I tutor, the harder it is for me to look up stuff. Because I don't know where it's at anymore. I've looked so long that, well, just a second, one more check. I want to check this because I guess we'll just have to go with that. Well, just because it's a function of x squared, that's still a function of x. So we did solve the problem, which was to express the area of an equilateral triangle as a function of x if the side length is 3x. So I gave it a side length of 3x. It's 1/2 the base times the height. Yeah. And that's 1 and 1/2 times 1 and 1/2, which is 2 and 2 1/4 times square root of 3x squared. All right, so that's our answer. Do we have an answer key at the end of this thing?
Check.
Well, we got a lot of questions on here. This is the review for the whole chapter test or whole course test. Final exam. Okay. I don't see an answer key, but that's okay. So far, I don't think we need one.
Yeah. These questions should be quick, though. They're not too difficult.
I'm satisfied with that answer. Okay, find the slope-intercept equation. Slope-intercept form is what?
Slope-intercept form is y equals mx plus b.
So that has an x-intercept of 4 and a y-intercept of 16.
Okay, so that means we plug in 16 for b and 4 for x.
Couple of ways we can do this. Couple of ways. There's our line. So what's the equation of that line? The simplest way I can think of to do it is to just look at that graph. What's b?
It's 16.
What's m?
M is
What's the slope of that line?
down 16 over 4.
Okay.
So that could be just 4.
Okay, but look at the line. Is that positive or negative?
That's negative, so it'll be negative 4.
It has to be negative 4. So that to me is the fastest way to do this. There is another way to do it, which would be put it into standard format. And standard format would say that the x-intercept is where y is 0. Actually, I'm not positive how to do it any other way.
Yeah. I think I know another way, but I think it looks just as well as the one you showed me.
This way I like the best because it's real easy to figure out what the y-intercept is and the slope just by looking at this.
And we can also use the x-intercept, plug in 0 for y and 4 for x and 16 for b. And so then that way.
Do what?
Plug in 0 for y, 4 for
starting with what function?
Y equals mx plus b still.
Okay, so starting with, oh, I see what you're going to do. Okay. Knowing that it's 16, okay, I like this. I like this. In other words, when I plug in 0 for y and 4 for x, then m ends up being minus 4. That's all I need. And then I've got y equals minus 4x plus 16. Yeah, that's a good technique also.
Hmm. So would this be q to q times e to the
Okay,
r
notice
to
that
the
it's not an exponential decay like it should be. Usually stuff depreciates exponentially. This is a linear depreciation. And what that means is that we buy it for 10,000 at time 0, and at time 4 it's going to be worth 3,000.
Mm-hmm.
So our function is going to be like this. And so we want the equation of that line.
Okay,
So V would be what?
E would be 10,000.
Well, 10,000 is the B. Okay, so that's mx plus 10,000.
Mm-hmm.
Only instead of x, we're going to use t. Now, how do we figure out m, the slope?
4 for T and 3,000 for V.
Well, or just figure out, look at and calculate the slope of this line.
Okay.
What's the slope of that line?
7,000. Yeah.
Okay, so V is equal to 7,000 over 4 times t plus 10,000. Now, the only thing we got wrong was the sign on the slope. It's got to be negative.
Mm-hmm.
Because once again, we can see that it's negative from our picture. Now, let's see if that thing works, because it's worth plugging in a value. When t is equal to 0, we get the value equals 10,000. That's correct. When t is equal to 4, t is in years. Well, the 4's cancel, and you have minus 7,000 plus 10,000. V is equal to 3,000 when t is equal to 4.
Yeah.
So we've got the equation right. And the biggest thing to check on this is to make sure you get the sign on this slope right.
Okay.
What's standard form?
What do I mean by standard form? Is it this right or that slope of this slope?
Well, I understood standard form to be this. Whoops. But when they're dealing with quadratics, I believe standard form is this.
Okay.
So let's express this in standard form of this type.
All right. So I'm a little lost still.
Okay, we're going to put everything on one side of the equation. So let's subtract y,
Okay.
and that leaves 0. And now we basically, that's standard form, only the number needs to be the right of the y. In other words, standard form would be x squared, there's no coefficient on x, plus 4x minus y, because there's no y squared term, plus 8 equals 0. That's standard form.
Okay. All right.
I think. Almost positive for a quadratic. Find any axis intercepts. What's the easiest intercept to find?
Let's see, the y-intercept.
What is that?
That would be 8.
And the x-intercept requires us to set this thing equal to 0 and solve it.
Mm-hmm. So, and this is backwards.
Notice that it does not factor nicely.
Yeah.
And in fact, since it does not factor nicely, rather than go directly into the quadratic formula, let's check the discriminant to see if it even has any real the discriminant being the part that is under the radical sign. If this is negative, it doesn't have any x-intercepts.
Okay.
And what is this?
Like 4, so B, so you get 16, minus 4 times 1 times 8, and minus 4 times 8 is 24. So this would be a negative number.
Since it's negative, this quadratic looks like this. It doesn't cross the x-axis. And it only has complex solutions. So you can have a lot of quadratics that have a y-intercept but do not have an x-intercept. And it's all dependent on that discriminant. Now, we saved ourselves a lot of time by not plugging it into the whole quadratic formula, which would have been our inclination. By just examining the discriminant, we were able to immediately tell that it has no real solution, only complex solutions. So what's the maximum value of the function?
Well, wouldn't be infinite, it's a maximum.
What's the maximum? I didn't quite hear you, Cameron.
It wouldn't be infinite, would it? We'd have to do something. It'd have to be something on the graph. Right?
Infinite is correct. If you look at that chart, there's no maximum.
Yeah.
What's the minimum?
Minimum would be 8. 0, 8.
Well, not necessarily. And the reason I say that is because that parabola is not necessarily symmetrical with the y-axis. It could be like this.
Okay.
In other words, that could be 8 there. We know the y-intercept is 8, but we want to know the y value at the vertex. So what's the vertex? Let's figure out the x-coordinate of the vertex.
We need to
minus b over 2a.
Okay. So yeah, minus 4 over 2, so negative 2.
And then what they want is the y-coordinate of the vertex, which would be the minimum value of the function.
Okay.
How do we get the y-coordinate of the vertex?
You just plug in negative 2 into the equation.
Okay, so that's 4 minus 8 plus 8 equals 4. So there's our answer, 4. So it was a parabola that was like this. Okay, it's asking me to shut off my camera, so I'll do that. All right. Okay, any questions on that problem?
Not really. I think I understand it.
Okay, I think there's calculus ways to figure out that maximum value, but at this point in pre-calc, the only way I know to get that minimum value is to find out where the vertex is and get both its x and its y coordinates.
All right.
What's the domain of this function?
Minus 11, so let's take a look. So it can't be 0, can you? Can't take the root of the 0, can you?
Okay.
Can't be 11.
It could be 11. Remember that the domain is all the allowable values for x. So let's take a systematic approach to this. I can tell that you were doing in your mind the same thing I was doing, which was running through the list of numbers that this could be or not be. But there's a better way to do this. Let's solve this problem. X squared minus 11, whatever's inside the radical, has to be greater than or equal to 0, correct?
Mm-hmm.
That's how we're going to solve the domain. So now let's solve this. This is not quite as easy as it seems. What's the next step?
Oh yeah, it's not.
You want to take the square root of both sides, but this is where it's tricky. In other words, one answer is x is greater than or equal to the square root of 11, but the other answer is not x is greater than or equal to negative square root 11, it's x is less than or equal to negative square root 11.
Okay.
And if you look back at the function, you can see why this is correct. If x is greater than square root 11, it makes what's inside the radical positive.
Mm-hmm.
And if x is less than that, make x negative square root of 12. Well, once you square it, it becomes positive 12, and then that makes that positive also. So the only numbers that don't work, if I'm on a number line, and there's 0, square root 11 is about here, negative square root 11 is about there. The only numbers that don't work are those.
Okay.
So interval notation would be negative infinity to negative square root 11 inclusive, combined with square root 11 a positive infinity. So there is your domain. But the real key in this problem, and I think this is a big understanding, is when you have a problem like that, do it algebraically. In other words, we know that if I've got some function under a radical sign, the domain of that function I can solve by doing this. And then whatever the function is, in our case the function is x squared minus 11. And then solve that. Now, I'm not sure we've actually encountered this before, but if I have a problem like x squared is greater than or equal to 4, then taking the square root, it's not so obvious what the final answer is. It's clear that x could be greater than or equal to 2. What isn't so clear is it's not greater than or equal to -2, but less than or equal to -2. So those 3 steps, make sure you understand them. When you have an inequality that you have to solve by taking the square root of both sides, you basically kind of have to assume that you're dividing by a positive number in the first step and dividing by a negative number in the second step.
All right.
Okay? I think you're pretty good with these. Do at least the first one. What is f of g? What is fog?
So that would be 3 over x squared minus x in parentheses minus 6.
Okay.
Yeah.
I'll trust that you know how to do. Oh no, I'm sorry. I thought the second part was what is the Goff? It wants the domain of fog.
Okay.
So
I think I can.
fog is that. Let's keep working on that. That's got to be x minus 3 times x minus 2. So this is fog. What's the domain of fog?
So it can't be 3 or 2, but
There's something else it can't be also. Can't be 6.
oh yes, that's right.
In other words, any domain restrictions on the original function has to stay in place. I think.
Okay.
I think. I've always been a little fuzzy on that point, to be honest with you. I think it's like a hole in a function. In other words, it's similar to this. If I have a function like this, well, clearly x can't be 1 or minus 1, right? But once I factor those out, now I've got this, and it looks like x could be 1. But you have to carry forth the original domain restrictions. So this function is not really equal to that. It's equal to that with the provision that x cannot be equal to plus 1. So I can't really say that this function that I started with, which originally would have been f of x equals x minus 1 over x squared minus 1. In other words, if this is my original function, that has a restriction on it that x cannot be equal to 1. And even though I factor the bottom and cancel out the x minus 1 on top and one of the x minus 1s on the bottom to produce this, I still have to carry that domain restriction with me. So not only can x no longer be equal to minus 1, but it can't be equal to 1 either. And in fact, if I was graphing that, I would have a hole in the hyperbola. at 1, right there.
Okay.
Okay? So this concept of carrying the domain restrictions forward even after you've modified a function, now it's real clear to me that in this case here that I was just describing to you, that's the case. I definitely have to carry that domain restriction forward as a whole. This I'm not as positive of. Clearly, when we get it in its final format, x cannot be equal to 3 or x cannot be equal to 2. As to whether x can be equal to 6 or not, I would love to know the answer to that. That may be something you should ask your teachers to the domain of number 11.
Okay.
And we'll find out conclusively whether 6 is excluded from the domain or not. I think it is. In other words, I think the domain of fog is all real except x can't be equal to 3, x can't be equal to 2, and x can't be equal to 6. It's possible that this last one is not part of the domain, but I believe that it is. I believe you have to carry forth those domain restrictions on composite functions, which is what this is. This is a composite function. Fog.
Okay.
Okay, what is A going to be? Can you describe it to me?
Let's see. F of x plus 1. Would that shift the graph up 1?
Yep.
Mm-hmm.
How about B?
B would shift the function, the x-axis, or all the points to the right 2 points.
Good. How about C?
Would that stretch the y-axis or the
Well,
-2?
it would change the shape of the function. It would no longer look semicircular. It would look like this. Because notice that every point that is now here would be twice as high. So this point that's on the axis would still be there. You multiply 0 times 2, it's still there. But if you take this point here, which is now at 1, multiply it by 2, this point would have to be 2, while this is still -1 and this is still +1. So it has the same effect as any vertical stretch.
Mm-hmm.
How about the last one?
Would that do the same thing as C?
Well, it's a horizontal stretch or shrink.
Mm-hmm.
And for horizontal stretches or shrinks, if the coefficient is greater than 1, it's a shrink. If it's between 0 and 1, it's a stretch. So you're absolutely right. It would do the same thing. It would be a horizontal stretch. The only thing is that it would, I believe, go from -1/2 to 1/2 and stay at 1. In other words, it would still change the shape of the thing into that, but it would shrink it horizontally.
Okay.
And if I start with this curve and I shrink it, then I have to bring the sides in. I don't take the top up. I bring the sides in.
Okay. One more.
Okay,
so it looks like f plus g would have to be 1 over x plus x over x minus h.
Okay, just for giggles, let's do that.
And then you multiply the...
What's the common denominator going to be?
X squared minus 8x.
X times x minus 8. That'll be the common denominator. So what's the numerator in the term on the left?
X minus 8.
And the numerator here?
And now the x squared.
So our answer that is f plus g. And notice that, in case you're wondering if that factors, it doesn't nicely. If it did, it might be useful to do so, because what if we found an x minus 8 as one of those factors, we could cancel it. But it doesn't factor, and in fact, I've never found those to factor. So, okay, f minus g would be exactly the same process, only you subtract the numerators instead of add them. What is f times g?
So that'd be 1 over x times x minus x over x minus 8. So you'd have 1. You'd have x over x squared minus 8x.
And before you do that, don't always distribute. Sometimes when you distribute, you're actually working against yourself. Simplify that. Notice that if I distribute it, the only way I can now solve it is to factor it again. So don't always distribute as a first step. Sometimes it's not the correct step. A function is actually more valuable in factored form than it is in distributed form. I mean, notice what you have to do to most quadratics. The first step usually is to factor them. Okay, and the last part, let's end it on, is what is f divided by g?
So that'll be 1 over x divided by x over x minus 8. And then you flip those and you get x minus 8 over x squared.
Okay. Very good.
All right. Okay.
Do you like this time on Fridays? When is this final? When do you have to prepare or be ready for this thing?
2 weeks from now, I believe.
Okay. Okay. When do you want another session?
We could do next week, and you can do your golf, so we can do it early in the morning. It's always since you just have to have everything ready.
You want Friday next week?
Yeah, because I'm busy Monday through Thursday pretty much the whole time.
Okay.
Yeah.
We'll just leave it on Fridays. In fact, you want me to lock this up for a couple of weeks, this time slot? Well, if you're taking this test in 2 weeks, you may only need one more session, you know. So
yeah,
I'm not worried about.
I might try to fit one in.
Yeah, I'm not worried about anybody taking this. I'm not worried about anybody taking this slot. I don't get a lot of demand on 10 o'clock on Fridays. So you can almost be guaranteed of always having this slot available. Okay. I will see you next Friday.
Yep, sounds good.
Okay, Cam. Talk to you later.
Yep.